Welcome to the 2022 Photonics Spectra Conference. You're joining us with Dr. Manija Razeghi, Walter P. Murphy Professor in the Department of Electrical Engineering and Computer Science and Director of the Center for Quantum Devices at Northwestern University. She joined Northwestern in 1991 and afterward created the school's undergraduate and graduate programs in solid-state engineering. She also funded the Center for Quantum Devices. Razeghi comes from a background in physics, and she's authored or co-authored over 1,000 papers, 35 book chapters, and 20 books. She holds more than 60 US patents and is fellow of IOP, APS, SPIE, Optica, and the IEC, and is a member of the Academy of Europe. Her awards include the IBM Europe Science and Technology Prize, the SWE Achievement Award, RF Bun Shah Award, IBM Faculty Award, Jan Trochowski Gold Medal, and the Benjamin Franklin Medal in Electrical Engineering. So in this keynote talk, she's going to be presenting future trends and the latest research breakthroughs that have brought semiconductor quantum engineering to new levels. If you have any questions or comments, please type those right into the conference chat box at any time. And if you miss part of this talk, you can come back later and watch it on demand. So I have nothing else for now. I would like to introduce Dr. Manija Razeghi. Welcome.
Good morning. I would like, first of all, to wish everybody and all of you Happy New Year's. And the talk, exactly as you can see, is the lasers, light amplification by stimulated emission of radiation. First, let's understand what does mean light. I would like to start by the periodic table and to say that the secret of science is in the periodic table, and understanding of the lasers can start by understanding the structure of atom. That it was the most important achievement of in physical science in the last century. It was understanding of the structure of atom, that is the basic, again, coming for the lasers, and that it was thanks to quantum mechanics. And as Niels Bohr say, anyone who is not shocked by quantum theory has not understood it. From the quantum mechanics, we understood that if we take atom of hydrogen, that is from one proton and one electron, this electron is moving around the nucleus that taking the energy from, and that is create the electric field. The spin of the electron that is running around the perpendicular to this direction create the magnetic field, and together create the electromagnetic field. And that, again, we understood can be wave or particle. This electron that take this energy permanently can move from the lower energy level, according to quantum mechanics, to the higher energy level, and that after that coming back and take this energy as a light or wave, and the wavelength of this light, that we can say that wave or photon, is proportional, after quantum mechanics, again, the Planck constant, velocity of light, and the energy of the initial and the final state of this electron. And that is the starting and the basic of the emission and detection, that we can take it after that to make it know the lasers. And how the three elements, as we can see here, becomes the fundamental of the active material, active devices, that is based transistor, lasers, and detector. And it was exactly as we can see here, this movement of the electron and the changing the energy can come from the X gamma UV visible, infrared, terahertz, up to the, again, millimeter. Nature help us to see and understand only a small part of this electromagnetic field. That is RGB, blue, green, red, only from 400 nanometer up to 700 nanometer. We are curious and we would like to understand and use again, taking the nature as an excellent inspiration source, our eyes, that is the best detector and the best sensor, the best again sensor that is catching and taking the difference element, can even detect the single photon. So in order to understand how we can make the emitter, it means that lasers, and the detector in the difference range, we need again to go back to the quantum mechanics. And one of the most interesting part of the quantum mechanics, it was understanding of the semiconductor. And just recently we understood that even any element with the single layer can be semiconductor, 2D material, and all of the difference. But my objective was, is, and continue to show that if we take a part of this element of the periodic table, column 3 and column 5, we can make the lasers. And of course, you cannot have the laser without detector, because for any lasers, any wavelength exactly as I showed in this view graph, we need to have at the same time the detector, and cannot be again without the transistor and the electron. So if we come now to the semiconductor and the difference element, and especially the emitter laser that is the subject of this talk, can be, if we come here, we can see that again in the need of any individual in the nature needs one of the, again, these lasers or detector for the difference wavelength. So my talk today, I would like to explain how taking the element of the column 3 and element of the column 5 and do again the gap and atomic engineering, we can make the semiconductor laser diode that did already and is doing and continue to revolutionize all of the need, and at the same time understanding of the, from the medicine, health, environmental, astrophysics, safety, anything that we want, we can have again to make a useful lasers. Again, I repeat, you cannot have lasers without, again, the detector, because that's the structure that are related. But the objective here is, again, the lasers. So I have to explain in order that everybody can understand. When we put the column 3, column 5, again, the binary, one of the column 3, one of the column 5, we say that binary, one of the, two of the column 3 or two of the column 5 and one with the other, and we can have the ternary, or two of two, we can have quaternary. So they are binary, ternary, quaternaries of this element of the column 3, 5. We are going to see that how, using the quantum mechanics, we can make very efficient lasers, again, from deep UV up to terahertz. And we have to know, in order to make this material according to quantum mechanics, to understand, to make them useful, we need to have to dope it It means that if you have 3,5 semiconductor, as an example, gallium and arsenide, if you are not doping, if they are perfect, we can do nothing with. In order to make them useful, we need to dope or N-type or P-type. We use one of the element as an example of the colon 2 or one of the element of colon 4 in order to decrease one electron. And in this case, we say that they are p-type because there is one electron less. Or we increase one of the element of the colon 6 or colon 4 to increase one electron. We say that no, they become n-type. And by manipulating this n and p-type carrier electron and the hole that is the empty space of the electron, exactly as I showed you in the first view graph, can have p-n junction, and by that we can manipulate to do forward bias to make lasers or to put reverse bias to make detector. Now, if we come here to see exactly as I mentioned, if the colon 3,5, if we put p-type or n-type, in this case, as we can see here, if we do reverse bias, we have detector. If we do forward bias, we can have the lasers or emitter. But in order to make them possible, again, last century, the most important part that make it possible, first it was the bulk crystal growth. Using the binary, one of the colon 3, one of the colon 5, silicon, but the gallium arsenide, or one of the colon 4, that colon 4 silicon or germanium or carbon. By that, we can have the support. And now we have the support in order to make the lasers and quantum device and atomic and gap engineering. We need to be able to manipulate the different element, different atom, and to be controlled atom by atom on this substrate or this support. So that is epitaxy. So during last century, many different kind of again, the epitaxy is invented and is developed. The simplest one, it was liquid phase epitaxy or vapor phase epitaxy, that both of them, they are simple, but unfortunately, simplicity always creates some problem. It means that they are thermodynamic equilibrium, but unfortunately, for the atomic and gap engineering, they are not very efficient. So now, after that, we have molecular beam epitaxy or metal organic vapor phase epitaxy, that they are far from thermodynamic equilibrium and that led to do atomic and gap engineering. It means that to be able to put atom by atom, that I'm going to show you how to make it, and to be able to do the different lasers, again from deep UV terahertz up to the terahertz. But unfortunately, again, this technique, they are not perfect. So you are going to see that how the new one of the, as an example, the technique that I developed is gas source molecular beam epitaxy, that bring the advantages of the both MBE and emissivity, and or MBE, metal organic molecular beam epitaxy, and all of that, that is, it was, it is, and it's important, not only for today, but for tomorrow, for the future. We need to have a big, really, the effort and study to come with the technique of the deposition. If we want go to, again, to quantum, it means that very small dimension, that is the subject of the talk, and at the same time the subject of the study of the word at this time. And another thing, it was the photolithography. So we put all of that together. We are coming now again to the quantum mechanics for the to make the again all of the atomic and gap engineering for to make the efficient lasers from deep UV up to terahertz. As I explained, if we are going to do the bulk material, first of all, let me to explain to you the column 4, that is silicon and germanium and carbon. Unfortunately, they are in direct gap, and at the same time they are covalent, of course, that is very important, and diamond structure, which make them excellent for the transistor, but unfortunately not for the optical. It means the optical device, it means that the lasers, because lasers need direct gap. So column 3,5 semiconductor, they have direct energy gap, they have covalent bonding, and they are most of them zinc blende structure. That is ideal again for to make lasers. Now, if I use only the bulk material, it means that binary, gallium arsenide, indium phosphide, etc., only the p-n junction. If I do again the lasers, as we can see here for the band structure, the density of a state as function of energy is parabolic. So my lasers is not going to be efficient. I have to spend a lot of energy in order that a little light is coming out. If I use now epitaxy, and I can do that quantum well, according to the quantum mechanics, I can have one-dimensional confinement for the electron. And in this case, the density of a state as function of energy, it becomes a step-lock behavior. So in one dimension, I can have much better confinement, and my lasers is going to be much more efficient. If I need here to put 1000 ampere per square centimeter for to have the lasers, here I need only maybe 10 times less. And now if I use not only epitaxy, but the photolithography, and I can do the two-dimensional confinement or quantum wire or artificial molecule, we can see that the density of a state as function of energy, it becomes much more focused, confined, and now I can have much better performance. It means that my laser can have much less energy to need in order to laser. But if I go to the three-dimensional confinement, it means that to the small, to confine the electron in the three dimension x, y, z, as we can see the density of a state as function of energy, it becomes much more focused. Or we say that is the artificial atom, like exactly the atom of the hydrogen that I showed. So in this case, we can have much better performance, and we need to have much less energy to put inside of the system to have the lasing, the red light is coming out. So as we can see here, the last century, we understood the structure of the semiconductor material. We understood the structure of the molecule. Now, by using again the new tools, we can make the artificial molecule or the quantum wire. And we can do the artificial atom, or the, in this case, all of them. We can make much better, much smaller, and much more stable and better performance, especially again, question is about lasers. So let me to explain again how I started that. In general, at the beginning, I was doing the no the atomic engineering, and I was very curious about the not only the structure of atom, but I was doing the neutron activation analysis, gamma spectroscopy, and using the studying the difference trace element in the cigarette and why, and I wanted to have the correlation between that and at the same time the cancer and the human health. But unfortunately, I got the high dose of the radioactivity and I have to stop, and I went to the solid state physics, phase transition. Phase transition in the lead phosphide, that is the perovskite. And the perovskite has the lower energy and they have always different phase change. So I use the different paramagnetic ions such as gadolinium, europium, manganese, and doing the electron spin resonance for to study the phase transition and understanding the calculation of the crystal field and at exactly what's going on. But again, application, everybody asking what's the application. But I was very curious about laser in general, lasers and the focal plane arrays, that how we could see in the at night and at the same time in the UV part. So that it was the reason after my science doctorate at Orsay University in France, in Paris, I went to Thomson CSF Central Research Lab at Orsay in order to learn about the technology for the 1 month because I have to be at university as a professor. And that there it was there at the that they become familiar with the again indium phosphide based for the telecommunication lasers for the telecommunication, that it was very very important. And the liquid phase epitaxy or vapor phase epitaxy, I don't know, they were using, and it was impossible to make the distributed feedback lasers for the telecommunication, and especially 1.3, 1.5. So that it was there that I went for the 1 month, but after 3 months, I make the world first emissivity 1.3 micron with emissivity that I didn't know even what that mean when I started. But with my background, I knew that if there is anything that anybody can do, if I like, I can make better. So that it was starting. So that I did that, and after that, exactly as you can see, is continue the 1991 at Northwestern. Again, they ask again as if that is the my about my talk. Exactly as you can see, that is 1976. It was neutron activation analysis, and 1981 electron spin resonance investigation of structural phase change. But after that, between 1980 and 1991, at Thomson, I created the exploratory material, and with the MOCVD, exactly the things that I did is in the book of MOCVD challenge that many the publisher they insisted, and I did with the IOP exactly. And this view graph that you can see here, that it was exactly each corner binary, each side ternary, inside quaternary, and the two system of the aluminium astronaut, gallium astronaut, gallium indium phosphide, this system, and the green system for the 1.3, 1.5 micron laser, that it was the things that I developed, I calculated, I understood. And this picture that you can see on the cover, that is the world first superlattice of indium phosphide, gallium indium astronaut, that revolutionized the world of the telecommunication. And at the same time, all of the results that I'm going to give you, not only for the 1.3 micron laser 1.4, but at the same time for the quantum cascade, and in the and is going and terrorize, and is going to continue. So now here, it was after that, of course, that during 10 years, I was only one at Thomson, that using at Thomson was only one to use emissivity and to have all of the 1.3, 1.5. Many places they wanted, and it was at Northwestern that the dean and provost and the president, they wanted exclusively to have this activity of the semiconductor at Northwestern. So they sent this picture, and it was on they were building the picture, the building just on the lake, and they thought if I'm coming, they give me the last floor of the building. With my experience during 10 years at Thomson, and I knew what we need because that this technology that I'm explaining to you, it is, and is continue. In 20 years, 50 years, all the time is like air and oxygen everybody needs. So for that, I try to build the facility from scratch exact. As you can see, the 3rd September 1991, the chair of the ECS came up with with his assistant at airport to bring me to bring me to Northwestern, and four, it was all of the material of my lab that removed and arrived at Northwestern. And I started the Center for Quantum Device at the time. And it's multidisciplinary because everything that I'm explaining, everything that you do, that is the multidisciplinary. And we need, again, for anything, we need to do first the theory, the modeling, understanding. And again, here I'm speaking only about the lasers, but the lasers cannot be without detector and without it. So that is for any lasers, any device, first to do the theory, after that material grows. Material grows exactly as I explained at the beginning. It's very important. Each material needs a special technique. And that is the important part that we have not to forget, that has to be to continue to revolutionize and to make it much more adaptable for the quantum device. All of the characterization. When you do the material, you need immediately characterization, optical, electrical, structural. We have to be very careful with the quantum device, with the structure of the laser sophisticated that we are doing. We have to have, is impossible one or two characterization can give the answer. We need more characterization, is more information. After that, of course, the fabrication. When we go to the quantum device, when you go to the different shape of the lasers, we need the different sophisticated equipment. And for that, in order to be sure that we can have all of the different possibility to manipulate, again, atom by atom, monolayer by monolayer. Now the measurements. When we do the quantum device, we need the different tool of the measurement, and we have to be sure that each system is 100% calibrated. We have everywhere in the US and in Europe at the same time, especially in US, we have many different great laboratories in the big company that they have expertise and knowledge. So it's very important to be sure that each system of the measurement to be adapted and to be calibrated with again the expert in US and in the world. And after that, of course, up to the system, because when you have the lasers and then you have again at the same time the detector, everything. So that I put everything together for one reason, because after my experience in France, that for everything that I was doing, I had to send the material to another laboratories for to make the device, another to do the measurement, and it was impossible, or to give, for example, to the some characterization for the electrical, or at the same time for the transmission electron microscope, etc. So that has to be, everything has to be in a perfectly in a closed packed, and to have rapid feedback of the material to the theory, characterization to the material, processing at the same time to the material, and to have the, in order to make a efficient and the result that I'm going to show you now. So exactly as you can see, I built that, and the less than 2 years, I did the inauguration of the center with, of course, Leo Isaki von Kliesing, that both of them, they are the father of the nanotechnology. And of course, with the dean and the provost, Jerry and Dean Cohen, that they were really the driving force and they wanted this activity. And that exactly, as you can see, that it was my group at the time immediately after. And here, the one that you can see here is a Steve Slivkan after 30 years that you know for the laser, as you know his name perfectly. Now, what I did at the same time, I tried to create the curriculum to have the solid state undergraduate, graduate. For the, you have to know that I never accepted to have the administrative, the job that they wanted very, very, as you can imagine. But my objective was to build this facility, and that it was the reason the administration and the dean, they understood, and they gave to my center a special statute that is unique, not only at Northwestern, in United States at the same time, because the center is like a department. So they did everything to let me to do the things that I did and I'm doing that can change, revolutionize really the world of the semiconductor lasers. So I created the solid state engineering curriculum, that this curriculum, and I created that the excellent faculty at the same time to teach each course that in. And I created for the textbook that the one of the solid state, again, fundamental of solid state engineering, that is the fourth edition just last year. More than 2 million copy, as is a Springer, 2 million copy is withdrawn. So for that, let me know to say exactly the outline of my talk, that is going from the UV to terahertz. I give you the lasers step by step. And I have to tell you, for each one that I'm giving you, I go, unfortunately, I have to go fast and not to the detail. But for each of them, I have the book, I have all of the, at the same time, the many publication that you can go and to see the detail, everything that you need. So let's say to start by UV. Why UV is important? If you look again at the ozone at 200, between 280, 320, the ozone is opaque. We cannot see above. So for many application, it's very important to have the UV lasers, of course, the detector at the same time, but lasers. But the most important part that I want to insist on, that at the present time with the COVID, that is one of the importance, is the bio fluorescence imaging. And that, if I come here to explain why it's important, because many biological agents, fluorescence, when excited by UV light, by combining UV emitters with UV detectors, it becomes possible to devise a compact system that can rapidly detect and identify certain biological agents based upon their fluorescence signature. So as you can see here, if we have one 280 nanometer LED or lasers, by shining a few molecules of anthrax, we can have the fluorescence, and if we have the detector, the base, the same wavelength, we can detect a few molecules of the anthrax rapidly. That it was exactly the subject that I started when I came at Northwestern. The first things that I started, it was the call from the DOD. They asked me, can you do aluminum nitride P-type? So some of you, you have to understand that aluminum nitride is the semiconductor, but indirect gap. But at the same time, is the gap is 6.2 electron volt. And now if we come with the gallium, and at the same time gallium nitride, and with the gallium and indium we do the alloys of binary or ternary or quaternaries, we can change the energy gap, and we can make the lasers and the detector from the deep UV 6 electron volt, 200 nanometer, come at the end of the interband or intersubband, go up to the terahertz. But the most important part is this part, but you have to know that still after 50, 60 years, importance of this material, nobody can make the substrate in the aluminum nitride or gallium nitride, despite that many different efforts. So that is again another subject of the research for the future. But the best substrate for that is sapphire, aluminum oxide, that is a woodside and have at the same time approximately the same, rather similar the lattice parameter. So it was for that immediately exactly the aluminum gallium indium arsenide, this quaternary and they have the woodside structure. So first I tried to develop a system of epitaxy because we do the calculation that is easy. So now, but after that, the publication. So that it was the reactor that I developed with extron. And still, after 30 years, anything that I'm doing and everything that I'm explaining is still in this reactor. So what we did, again, we tried to grow, to do atomic and gap engineering from aluminum nitride, that is 209, and coming by the ternary, quaternary up to gallium nitride, and to put indium and ternary and to the, that is the photoluminescence. Exactly as you can see that we can go from 290 up to the again visible 400, and by intersubband we can go up to again up to the terahertz. So after that is the exactly the growth of this material. That is very important. How we can make now the LED lasers and detector. So that again is the theory, is the quantum mechanics, is the confinement and optimization of the structure. So you do the optimization, that is the theory part, not the growth, and that is the growth exactly as you can see here. I put that here on silicon substrate. You have to know that all of this result is the for not only for the first time in the board, but still they are unique, and that is the future. It's not only now. Again, everything that I'm explaining to you, that is the hot subject and is continued to be again as lock, air, and oxygen. So now we did the LEDs, but at the same time, we make exactly the structure of the LEDs and detector and lasers, exactly as I mentioned, forward and reverse bias, but of course, by a little changing the thickness. Here we demonstrated that's the responsivity as function of wavelength for the difference detector. And as you can see here, that is the quantum efficiency. And my student Danielle Walker, that it was her work. Now she is the vice president of Global GE, and all of them that you can see here, all of them they are the great professor. But the subject is still hot, and the new student, and we are working on that. But what's the important? Look at here. I mentioned that the material, when you do the structure, because all of the material that we are growing here for the LED and laser, all of the layer, they are lattice mismatch with each other. And lattice mismatch, it means that create the defect. The defect, each defect kill the lasers in continuous wave and increase the dark current for the detector. So the material and the optimization of the material understanding is very important. Here that we have the sapphire substrate, that is the work of two of my students, Ali Reza Yassan, and at the same time the Ryan McIntosh, that as you can see here, that and the transmission electron microscope done at Northwestern in the Professor Dravis group, for sapphire substrate is the wood side. Aluminum nitride is wood side. But there are lattice mismatch. Every 9 plane of sapphire is equivalent to the 8 plane of aluminum nitride. And when you are growing one over the other, you have 30 degree, again, lattice turning by comparison to the substrate. As you can see here, every 9 plane, we have one edge dislocation. And that is the perfection. And after that, as you can see, no defect after that on top of that. Of course, as you can see here, after that, of course, that you are increasing again the lattice mismatch because it's a very sophisticated that we have to do. But the beauty of this material is, as it's a large bond gap, very, very strong covalent, the mobility of the defect is very low. So we can make, again, the LED and we can make the laser. That it was the things that we did. The world first 200, 308 to 40 nanometer, 280 nanometer, 256, 254, and that equivalent at exactly we did the detector, and for that, all of that, as you can see, for the difference agent, and especially for the anthrax 280 nanometer, that it was very important, and DARPA put immediately the BAA, and it was very hot subject, and we demonstrated one after each other. So last year, just recently, we are doing gallium oxide, that is the, again, wide bond gap. And the question was, what is the important? I explained that for the coronavirus, that is important to study this material at the present time for the coronavirus. Of course, many, they could not really even understand, but immediately the Japanese and Korea, the Nisha use 280 nanometer deep UV LED for to eliminate up to 99.99% of SARS-CoV-2. And Seoul, they try to show that by using the LED, UV LED, they can provide 99% surface disinfection of the COVID-19. So you can see that how this material is important exactly after that. When you can control the material, you can make the lasers, and that it was, again, the first lasers in 1993 came from Nishio, and the second in the world, it was from my group, as you can see, and it was a lot of publicity, a lot of problem behind. Nobody could believe, but they sent here the expert to come, and we sent the material to the difference in Cornell University in France, everywhere, to say that yes, it's blue laser. Nobody could believe. So now, with the inter subband, with this material, we can go again the longer wavelength. And at the same time, in order to go for the lasers inter subband at the same time, one of the important elements is to have resonance tunneling in this material. As again, as I mentioned, all of that, they are lattice mismatch, and we have not, again, the substrate, neither gallium nitride or aluminum nitride. We have to use sapphire substrate or silicon substrate. So that, but when you use gallium nitride, they, as a, because now they do the gallium nitride substrate, they grown the gallium nitride very thick layers with the vapor phase epitaxy. After that, they slice and they polish, and they have, again, the gallium nitride as a substrate. But when you use that, in this case, as we can see, we can have the resonance tunneling in this material, and that what is important, because at the present time, for the teraized lasers, that is very teraized laser dye, that is very important. Unfortunately, we are using the gallium nitride or the gallium arsenide and or indiophosphate. So the allophonon of the gallium nitride, gallium arsenide or indiophosphate is a very low energy, 36 millielectron volt, and KT is about 25 millielectron volt. But when we go to the trinitride, gallium nitride, the allophonon is 91 millielectron volt, much higher than again the at the room temperature 24. So that is the excellent, again, one of the important for the future study of the inter-subband for the terrorists. So that is the future. So I want to say that in 1993, when I came to Northwestern, starting by aluminum nitride, and exactly as you can see up to now, that I didn't put that here at the same time, is continuing. We did one by one a study published and at the same time to demonstrate that with this material, of course, the work of the Nakamura, that it was from the nitride, gallium nitride, gallium indium nitride. But everything from aluminium nitride, aluminium gallium nitride is developed in my group. The patent of the PTOD, aluminium gallium nitride, it was my patent. Unfortunately, Northwestern couldn't understand at the time the value. It was too early, so they didn't continue. So we demonstrate all of that. And at the present time, again, that is the very hot subject. And we are doing, in my group, we developed already the Geiger mode single photon detection in gallium nitride long time ago. We developed focal plan arrays again at the 280 nanometer. The we publish, and at the present time, our work, we are doing the single photon and a Geiger mode for the UV, deep UV, that is the very hot subject. And as I explained to you, again, the LED and laser diode in the UV for the different application, but especially for the coronavirus and the difference, again, the different kind of the virus that are coming, that all of them, they have the different kind of the protein that needs to be detected. So that is a very hot subject. So now I would like to go to the next stage. It means that to 800 and 980 nanometer lasers. Why? Because the application is very, very important. And that before again, since because all of the things that I'm telling is the work that since 80 last century, everybody after quantum mechanics understood and are working. But unfortunately, again, it's not easy because needs to have not only the theoretical background, but at the same time, the how to make it. So again, all of the information I revolutionized 808, 980 nanometer by aluminium free, gallium, indium astronaut, phosphate, gallium astronaut, that at the same time, all of the information is in this book, the emissivity challenge, that is with the IOP, but I would like only to show you here what was that, because for the telecom, pump lasers, and many different applications, they were using gallium astronaut, gallium aluminium astronaut, with the MBE, that it was expensive, and due to the aluminium, the problem, the material, the laser, it was not, it was catastrophic optical damage, and what they needed, it was very expensive. I developed aluminium free with the emissivity, and that revolutionized, exactly as you can see. I did that 94. I published in Nature, and that the lifetime become, as you can see here, forever, and the excellent performance for the high power lasers, and at the same time, as you can see, is revolutionized. So that is the part and the information again, and that is continuing because that is the material of the day, the difference again, the activity difference performance of the for the telecom and for the many difference again, high power, etc. Now I'm coming to the infrared 1.3, 1.5 micron. That's again for the telecom, it's not new. It means that 50, 60 years, everybody, especially in US at Bell Lab, especially for the telecom, and the Japanese, all of that they are working. But what was again the problem? It was again using liquid phase epitaxy or vapor phase epitaxy, and it was impossible to have the DFB. So again, that is again, as you can see, all of the information is in this book, that the MOCVD challenge. So for the 1.35, 1.5 micron, that is for the silica optical fiber, that they were using liquid phase epitaxy, and that it was the problem. It was liquid phase epitaxy. You cannot grow the high the wide band gap material into phosphate on gallium indium arsenide. So that it was a big problem. So I developed emissivity, and at the same time with the quaternary, with on indium phosphate substrate, and that it exactly as you can see here, that it was the first DFB, and that this result at the same time, it's old, but it was everywhere. That is revolution. They bring the result, the price of the DFB from the $100,000 to become to the a few $100, as you can imagine. And at the time, I put that on silicon substrate, and I demonstrated by a few monolayer at the interface between indium phosphide and silicon substrate, we can have excellent result. That is the excellent result that you can see with the continuous wave. And they were telling, because that is measured at the same time at in CNET in France, that they are again the expert in the telecom, and they were telling that this laser is good because it's on silicon. And you know that now, after approximately 35, 40 years, the dream of everywhere and everybody is to put everything on silicon, and especially the laser. I'm going not to the last part. It means that each laser, each wavelength is important. So we came for the infrared 3.3, 3.3 micron, and up to that exactly they're using interband. Again, that it was the high power indium antimonide between 3 to 5. That is the result that is published by the Army Research Office. But unfortunately, at this time, it was intersub-band, and the government, that the Durvasula and Henry Everett from the Air Force and from the DARPA, they came to ask me to be involved of the quantum cascade. Quantum cascade is and everything again is in this book. The result, I'm not going to the detail, and you can see that again is the more than 2 million again copy came out in a spring. So you can have all of the physics behind of that. So the application is normal. We know that. So what is the difference? Up to know everything, it was everything, it was direct gap. Okay, it's not is okay, everything is the interband. But when we go to the longer wavelength, it becomes intersubband. And intersubband, again, we can use indium phosphide material, gallium indium arsenide phosphide, exactly. And to do at the same time the strength balancing, it means that to manipulate the structure for to have exactly the wavelength that we want and the performance. And it was here and doing exactly the band structure calculation, waveguide modeling, thermal analysis, and using that again, because the first, again, the electrical injection, it came from Bell Labs, that they did low temperature and at the same time low power, because they were using MBE. And at the same time, and when government asked me to be involved, immediately I used the gas source molecular beam epitaxy, and exactly as you can see here, and to do it characterization, optical, electrical, structural, and the fabrication, everything. And to come immediately after 1 month, exactly, we developed, and that it was in the photonic again, as you can see that the 1997, the world first that they did the publicity for that. And from the 3 micron up to 12 micron up to today, we have the record of the continuous wave, power, single mode. And at the same time, during 5 years, my group was only one in the world to have the continuous wave, high power at room temperature, and convince not only the government and the different group, different company in the world, to see that that is the right way to go. Now I go very fast only to give some of the highlight. We need high power, high ball plug efficiency, continuous wave, room temperature from the short, mid, and long. Here you can see that here at 4.4 micron, 34 watts for photonic crystal distributed feedback. Single mode far field, single mode telegraph. You can see that 203 watts for single diodes with the excellent performance. All of that is published, and all of that is future, because I do one demonstration that is future. And now I gave it exactly, because for the blue laser, nobody could believe I gave it two again daylight. That is the result of Northwestern. That is the result of daylight. Conclusion, as you can see here, they measured higher power. And this result, as you can see, not only after 11 years that it was the record in the world. The new record, we just got some funding from the in, and as you can see, all of that is the new record of the year. But unfortunately, everything it becomes now for the high power, the lasers, and it becomes the ether, and I cannot more to speak about the new result. But here, instead of the quantum cascade at long wavelength infrared, as you can see, at 8 micron, 20% wall plug efficiency and excellent continuous wave. As you can see, all of that, they are new, they are results, but it's sure that if we did, everybody can do, and they are a lot of application. No high power QCL master oscillator power amplifier that everybody needs in the industry. I demonstrated here we can have 3.8 micron, 4.6 micron, 8 micron, single mode, high power continuous wave. So that all of that is the game changing for the future. Now coming to the monolithically widely tunable, because that again, it was again with the Homeland Security that they wanted one system to come for the explosive detection between 6 to 10 micron. That exactly, as you can see, that we try to develop, and I encourage you to look again on the publication and the results. So that is very, very important, and that is again future, and many great group in the world, they are working at the same time on that. No monolithic steering with the surface emitting. Yes, that is the first monolithic steering. We need the steering. I'm not going to the detail. You can go again to the publication, but you can see that that again is the future. Now we go to the again the first integration again for the phase arrays. Again, as you can see here, that is the lateral steering video. That if it's working, yes, exactly, and all of that that you can see, we demonstrated that is possible. Unfortunately, most of this result it becomes now the ether control, and I cannot come to the new result to show you. So the silicon photonic high power phase lock QCL based on optical phase arrays. So as you can see again, that is the word: long wavelength, continuous wave power, phase locked QCL arrays with the 8 again, the the MMI. As you can see here, we have the spectral line with only 1.2 nanometer, and the far field is only 0.5 in continuous wave and single mode. And you can see that, but what is the again all of the application for the future. Now go to the high power long wavelength mid short laser amplifiers. Again, for that we give again all of that that you can see, that is the world first with the single mode 16 element high power based phase lock, and that's the 50 51 watt at 8 micron, and 3 at 20 watt at 3.8 micron, 30 watt at 4.8 micron, and the single mode exactly. So all of that, that they are the future. Now I'm going only to the last part. Terahertz, we know that how the terahertz is important, but this what is the problem? We need the source of the single again, the diode. That it was again, that is based on the nonlinear process, and that we can have again by optimizing that in the intercept, and we can have terahertz and at the same time frequency comb. So we demonstrated that is the word first. Not only we demonstrated continuously, but the beauty of that is, as is the DFG, it means that difference frequency generation as function of temperature, as function of the injection power, there is no jump, is fixed. So for the telecom and for the telecommunication, it's so important. So all of that again that look at here, we have again is the very interesting 1.9. Now we have much more higher at the same time, but this that is the far field only 12.5 degree, and is a continuous wave again, and that is all of that. It was the highlight of the nature photonic, and that how we can go now further, because for the future toward the 100 milliwatt, exactly as I showed that here, that is the future. We can go by using again the phase lock arrays, we can go up to 100 milliwatt. So that is the future direction. Now going to the high power frequency comb. I'm not going to the frequency comb in, I'm going to the exactly the new result that we did, the world first terahertz comb operation at room temperature. And that is by using that, we try to use again the largely detuned the DFB grating with respect to the gain peak in the it will be integrated into crucial cavity, and we provide a single mode operation at Lambda 1 and with the and doing the DFG between Lambda 1 and Lambda 2. We demonstrated again world first room temperature rise frequency comb. I'm not going to the detail. You can see that again the result because it was the highlight of the Nature Photonics at the same time. So all of the device that I showed you, without exception, it's not only for the publication. The things that I do, the gap between research, development, and production is very narrow. All of this laser that is there at more than 1 watt at 100 degrees C, by doing the power cycling every 30 minutes, as we can see, there is no degradation, and all of that is, but we need to know the coating, AR coating, HR coating, a pizza done. Each step is important. And by that, again, we did the world first, 1997, that it was published and they published in Photonics. And now, up to now 23, everything that you can see in red, or is the first, or is the record. And that is the future again. Everything that I did in France 30 years ago, now it becomes important. And all of this result, you are going to see that because great people working on that in 20, 30 years, all of that did become important. So what does the future hold? Exactly. Fundamentally, nature operates on the quantum level and is full of wondrous uses of quantum technology. So what we need to do, we need at the present time, how we can go to the quantum wire, quantum dots, and artificial atom, and to put everything on silicon. So for that, I would like to conclude and to do the perspective for the lasers at CQD Northwestern. We did the breakthrough in 3.5-based laser diode from UV to trials at room temperature continuous phase. We have to continue all of the group in the world in this area for the high power, high ballpark efficiency, single mode, wide spectral range from UV to TRIS, monolithic integration of multiple element for wide tuning and outcoupling, room temperature, high power TRIS source and frequency comb based on DFG will push this technology to new frontier of research. Many new applications will emerge in the near future. And by that, I would like to stop and to say, all right, thanks for your attention. Okay, my dear.
Thank you very much, Dr. Razeghi. That was an excellent overview. And thank you everyone in the audience for your questions and comments. If you haven't left those already, you can type them into the conference chat box at any time. And thanks for joining us for the present and future of quantum semiconductor laser diodes from UV 2 terahertz. This is again part of the Photonics Spectra conference, which is hosted by us at Photonics Media. And you've just heard from Dr. Manija Razeghi of Northwestern University. Thank you so much.